This dashboard tracks 3 metrics from the May 14th Autonomi Testnet update. We are seeing downloads 2 to 3 times faster, 0 failure rates on 1 GB uploads, and millions of concurrent pub/sub subscribers. In decentralized storage, high throughput and network overhead usually share an inverse relationship. As more data moves across distributed nodes, the management required to track that data typically degrades the system's overall performance. Resolving this friction usually requires centralized oversight to manage routing and validation. The fact that the Autonomi Testnet achieved these metrics without a central coordinator makes these numbers anomalous. These efficiency gains come from a combination of client-side optimization and a specific approach to state management. 2 architectural shifts are driving this performance: dynamic decryption batching and Merkle-Based payment caching. We are watching a clear transition in the codebase. The development focus has moved past feature implementation and directly into network stress tolerance. For engineers building scalable, trustless storage networks, understanding the mechanics underneath these metrics is crucial. Let's start with data retrieval. In recent benchmarks, the time required to process a 171 megabyte file dropped from nearly 3 minutes down to roughly 1 minute. The delay in the legacy architecture came from static client-side limits enforced during the decryption phase. This architecture model shows how fixed memory buffers create a bottleneck. The decryption process chokes on a static limit, creating a data traffic jam. The solution is scaling batch sizes dynamically. The client reads real-time memory availability, expanding or contracting processing buffers to match. By removing the artificial memory ceiling, the client processes decryption batches as fast as the hardware allows, accelerating the entire retrieval phase. There is a technical nuance here regarding the current release cycle and the exact origin of these speed improvements. The current 2 to 3 times speedup is driven by underlying stability fixes running in the release candidate currently on production, not the batching update itself. The pull request containing the dynamic batching logic is slated to deploy in the next release. When that dynamic batching code goes live, its efficiency will compound on top of the stability-driven speed gains already recorded on the testnet. Client-side memory elasticity is as critical to decentralized retrieval speeds as raw network throughput. Moving from data retrieval to data ingestion, the testnet is now registering a 0 failure rate for 1 gigabyte file uploads. This solves the primary flaw of monolithic large file uploads in distributed systems. In this diagram of a monolithic transfer, any dropped connection ruins the entire process. If the transfer fails midway, the client drops the file, resets progress to 0, and wastes all expended bandwidth. To engineer around this fragility, the architecture utilizes Merkle-Based Payments. Watch the system split the 1 gigabyte file into smaller chunks. These act as leaf nodes, linked upward via cryptographic hashes to form a Merkle tree structure. This allows the network to cryptographically verify individual chunks independently, scanning specific leaf nodes against the hash. Because of this independent verification, the network never needs to process the entire 1 gigabyte file at a single time. Architecturally, this explicitly decouples the payment state from the overall upload process. The network only demands payment for the specific, cryptographically verified chunks that successfully transfer, rather than requiring upfront payment for the whole file. Chunking the data and mapping it to a Merkle route is the absolute prerequisite for enabling trustless, piecemeal data ingestion. This piecemeal ingestion poses a secondary problem. If an upload drops midway, how do you ensure the user isn't forced to pay twice for the same data when they retry? This diagram tracks a network failure during a Merkle-based upload. The transfer is interrupted. Successful nodes turn green. Pending nodes turn red. To solve double payment, the payment state for successful green chunks is cached locally on the client. This changes the mechanics of restarting a failed upload. When the user initiates a retry, the client references its localized cache to prove that payment was already rendered for the existing green chunks. This cryptographic proof strictly satisfies the network's trust requirements for those specific nodes. Because the network trusts the cache, the upload resumes exactly at the failure point. The system only processes and charges for the remaining red nodes. Users are no longer financially penalized when their local connection drops or the network experiences instability. This localized, verifiable caching is the exact mechanism enabling those 0 failure 1 gigabyte uploads on the testnet. True resumability in a Web3 environment requires cryptographically shielding the user from the financial penalties of dropped connections. Beyond client-level optimizations, the team is actively validating broader network stress tolerance, specifically focusing on the X0X messaging update. This topology map illustrates the scale of the 2-week pub/sub/soak testing. The protocol successfully managed the load of millions of concurrent subscribers per topic. Completing this messaging architecture validation means the testing cycle can now shift upward to the application layer. Concurrently, developments on the trust layer are moving forward. A proof-of-concept marketplace contract is now deployed to the blockchain and is undergoing adversarial review. Rigorously stress testing both the messaging layer and these economic contracts is mandatory before the network can transition to market-based pricing and a final production environment. This unified architecture stack represents the 3 distinct vectors covered in the recent update: dynamic memory allocation, stateful Merkle payments, and pub/sub scale testing. Collectively, these components resolve the historical speed and scaling bottlenecks that have traditionally held back decentralized storage systems. The raw testnet metrics confirm that these are no longer theoretical concepts. They are stabilized core primitives operating under stress. With the base layer stabilized, the focus now moves toward app layer integrations. Specifically, the indelible and reading room applications are the next major integration milestones to track. The team has explicitly stated a shift in their communication strategy, moving away from sharing future intentions to focus strictly on reporting actionable engineering results as they occur. The recent metrics show the network moving beyond basic feature implementation into a phase